really had all to do with the illustrations, because I couldn't see what the teacher was going for when it came to this sort of thing. So I'll see if I have an applet. I'm pretty sure I do somewhere. Just a matter of pulling it up. I think I have something on GeoGebra. But the do now, write an expression to find the area of the region bounded by the axes, and lots of meh. So we have y equals the cube root of x, the axes, and x equals 8. All right, so the bounded region is entirely adjacent to the x-axis, so it makes sense to integrate this with respect to x. So I'll draw my arbitrary rectangle with respect to x. All right, so that's my rectangle, my lazy rectangle. I'll do my dx there. We know that it's going over the interval of 0 to 8. It's entirely bounded by the function, which is the cube root of x. Dx. Right, the area of that arbitrary rectangle is base times height. Base is dx, height is y, right? And I'm going back to that idea, so being a little bit more detailed because it's going to play into our discussions revolving around revolutions. So the area of this rectangle is dx times y, with y being specifically the cube root of x. Right? So it goes back to the idea that any distance in space can be represented by x and y, x comma y, the ordered pair, where x is the distance from the y-axis and y is the distance from the x-axis. All right, so that's going to be an important idea moving forward. All right, so what if this area was rotated around the x-axis? What would be the volume of this new figure? All right, so I'm going to draw that bounded area again. Just the important parts, though. All right, I'm going to spin it around the x-axis. So I'll draw my little symbol to represent the spin. I do that as a reminder to myself which way I'm going with it, because you see in the next part, we're going to revolve it around the y-axis, and then we'll do it around another non-axis, so another line. Right? So we're going to take this region and spin it around so that it creates a surface, right? A three-dimensional surface. Right? So basically, this little area is going to populate infinitely in all directions, with this axis being its center. All right. So the one obvious case, if we're just going case by case, would be down below the x-axis. You'd have one jutting outward from the x-axis. You'd have one at maybe like a 30-degree angle, maybe the other way. You'd have it going back into the page. You'd have all sorts of possibilities. But it would create a circular path. All right, so, and this is where the drawings come into play. So it would look something like this.
It's like half an onion. No.
I had everything going well, and then I tried to make, I'm just going to leave that dashed. So there's that. Now, let me see. All right, so now, okay, now we know what it looks like. Now we know what it looks like, so let's try to come up with a volume of this. Now, hopefully you got out of all of that is that there's a circle involved, all right? So I'm going to streamline this picture again to really just consider the main structure of it, which is the function itself and the relevant boundaries. All right, now that function again is y equals the cube root of x. I want to take that again and spin it around the axis. In order to do that, what I essentially need to do is create circular disks. That's why it's called the disk method. All right. So I'm going to take an arbitrary rectangle on this interval, just like we did in the do now. All right. So I'm going to draw my lazy arbitrary rectangle. I'm going to label it up, dx and y. If I just integrated this, well then I wouldn't get what I wanted because I already know what that would give me. That would give me the area in the bounded region. What I want to do is I want to spin this around the axis. All right. If I were to spin this around the axis, what figure would it create? A circle, all right? A circular disc, but more basically a circle. So a circle with thickness. All right. So I'm going to try to draw that.
But a circle's not three-dimensional or two-dimensional.
That's what I'm saying, a circle with thickness. So the cylinder, yeah. Now what I actively try to avoid, now this will seem nitpicky, I actively try to avoid using the term cylinder for this particular topic only because there is a technique called cylindrical shells which works completely differently. And if you start thinking cylinder here, it might send you off on a different path. All right, so anyway, I need to come up with the volume of a single disc, a single circular disc. All right, I'm going to draw it with a little bit of thickness. Just to emphasize that part because it just felt naked without it. The area of the circle, just any circle, would be pi r squared. We know that. What would be the area of this circle? Pi y squared. All right. Now, as perspective drawings go, obviously this isn't the best, but the thickness of that arbitrary rectangle, that rectangle is what gets spun around and gives the disk its thickness. So whatever the thickness is for that rectangle, that ends up being the thickness for the disk itself. All right, so if I want the volume, I'm going to end up with pi y squared multiplied by the thickness dx.
Why did you choose to write y squared when you can write x squared for 2/3?
There's a pretty solid reason for that. It has to do with first the drawing, but also we want to have a generalized model, and then after that we'll put in the actual function. Now later on, when we're actually subtracting, because the washer method, which is the extension of this, involves subtracting another region from the given region, it becomes easier to work with it in general terms. Right. So now I can set up my integral because pi y squared dx gives me the volume of that single circular disk. Now I just want to collect all of them and add them together. And that happens over the interval of 0 to 8. So 0 to 8 pi y squared. Now I could put in the real y. Dx. All right. So that's what we would be using to compute the volume of this solid. All right. Which is pretty easy to do. I mean, it's just antiderivative, plug and chug, call it a day. All right. Now, I want to take that, for the second part, I want to take that and spin it around the y-axis. All right, yeah, so that vertical line is kind of confusing, so I just took it out. So we're taking this and spinning it around the y-axis, all right? Or at least that's what the intention of the question was. Because if it were that actual bounded region, then it would be washer method, and we're not there yet, all right? So, I think I need a rephrase on this question. Yeah, I think that's just all there is to it. Yeah, I would want it to say bounded by y equals 2 instead of the x equals 8. So I'll make the adjustment from there. All right. Because it's this region. Let me clean it up a little bit. This region that I wanted to spin. All right. So either you got the typo or I'm having a stroke. Because my left leg just started spazzing out.
Everyone immediately, no hesitation, very quietly.
Like the entire class did. Except so I'm gonna spin this around, but what that means is that I need an arbitrary rectangle that's perpendicular to the y-axis. So again, my lazy arbitrary rectangle with a thickness dy and a length dx. All right.
Wait, why is there a dy and a dy and dx? It's just x. Oh, it's just x? Oh, it's just dx.
I might have said dx. I feel like I said that.
Okay, now I got it.
Shockingly, I wrote the right thing though. Yeah, like. That's why I need a TA. Just quality control really more than anything else. But of course that would be a case where it would work against me because I would have said the wrong thing. Yeah. Whatever. So anyway, this interval is going from 0 to 2. Now if I were to spin this around the axis, I'd get a top looking thing or inverted cone kind of thing. In terms of a drawing, it's going to be terrible because I've never successfully pulled this one off. Yeah, that's the best I can do, I think. Because after that, it's just going to make it too messy. It's like a tornado-looking kind of thing is what I'm going for, you know. But not like a regular circle, more like a freaky circle. All right, so this is going from 0 to 2, because it's with respect to y. Area of a circle is pi r squared, so this would be pi times the radius, which is now x squared, times the thickness dy. All right. I like doing it this way. This is what I was talking about before. I like doing it this way to start because this gives me a recipe to get a sense of what I'm looking for in terms of my function, right? Because I was given the equation y equals the cube root of x. But I need an x equation. I need an x function, which means I have to solve this for x. X is equal to what? Y cubed. All right. So on the interval of 0 to 2, pi times y cubed squared, or y to the 6th if you want, dy. All right. by solving that, you'll get the volume of this figure. And, you know, we're revolving it around two different axes, so don't expect the volumes to be the same. That's a common question that I've gotten in the past, should they be the same? Well, they're two different shapes, so, you know, the expectation that they would be the same is, you know, it should not be there, you know? Like if I handed you two geometric figures, a circle and a square, yeah, they could have the same volume, but the likelihood that they do, I don't know. I wouldn't bet the farm on it, you know. So that's the idea there. Now I'm going to spin around the line x equals 8. All right. So I'm going to take the function, just the function, and spin it around the line x equals 8. So here I'm going to draw the entire function, or maybe not the entire function, a good chunk of it. Maybe not. I'll just draw that part. But I'll draw the entire vertical line x equals 8 and draw my little spin icon. All right, so it's the same bounded region from the do now in the first problem, but now I'm spinning it the other way. I'm spinning it around that vertical line x equals 8. All right. Either this topic is really easy, or some of us have just decided to take the L. So this is what the figure ought to be, something along those lines, kind of like a beanie. All right, so we just have to consider what would represent the radius of the function as it's being spun around the axis. All right, so now you don't always have to draw the three-dimensional figure to get a sense of what's going on. Actually, in all honesty, you hardly ever have to. It's really the original function and the axis of revolution that you need to draw to get a sense of what's going on. All right, so my radius should extend from the axis, so lazy rectangle, to the function itself. So here I have a thickness dy, but this rectangle does not have a length equal to x. All right, because remember I was talking about this before. X is the distance from the y-axis. So I know that this distance here is 8. So what's the length of my rectangle? 8 minus x. And that's because the distance from the y-axis to the point in space is x. So x would be pretty much everything you don't want in this case. 8 minus x is the part that you do want. All right, so 8 minus x would represent the radius. So in this case, I would say that in terms of y, I'm still going from 0 to 2. Pi r squared would now become pi times 8 minus x squared dy, with the adjustment being that x is equivalent to y cubed. So on the interval of 0 to 2, pi times 8 minus y cubed quantity squared dy. All right, so same function, different axis of revolution in each case, therefore different volumes, or potentially different volumes. All right. But all having to do with what you define as the radius. I might snag some time tomorrow to talk about the second fundamental theorem. We'll see. But you probably are going to have more questions related to volumes for me to go over, so I'll take time. All right, so let R be the region between the graphs of y equals 1 and y equals the sine of x from 0 to pi over 2. What's the volume of the solid obtained by revolving around the x-axis? All right, the washer method happens when there's a gap of some kind between the function and the bounded region and the axis of revolution. All right, so we're going to draw the graph. We have y equals 1. Y equals a sine of x over the interval of 0 to pi over 2. All right, so I'll draw pi over 2 here, for example. The sine function hits its max at pi over 2, starting at the origin, so that's really what our function would look like, or at least the relevant portions of it. I don't think there's a way I could sneak in the y equals sine of x there, so I'm just not even going to bother. Right? We're going to spin this around the x-axis. So here's x, and that's our axis of revolution. All right. If I were spinning this around the y-axis, like let's say it was just this triangular region, perfectly fine, disk method. There's no gap between the bounded area and the axis of revolution. But by spinning it around the x-axis, there is a gap. And that's a problem, right? Because if I were to define my radius as the distance from the x-axis to that function here, that would actually give me the part that I don't want. But the good news is, that's pretty much how you do it anyway. Because what we're going to do is we're going to apply the disk method twice. That's what the washer method is. It's the disk method twice, where you find the volume created by revolving the outermost function. So I'll create an arbitrary rectangle for the outermost function around the axis of revolution, and subtract from that the volume created by revolving the innermost function around the axis of revolution. So what's going to happen here is I'm going to get a y value for this guy with a dx, and I'm going to get a y value for this one also with a dx. So two different y values. Particular to their functions. All right, so it's kind of like basically saying, I equate it to, is it called a pottery wheel? What's the thing, like, is that what it's called? Okay. Yeah, you got the clay, is it clay?
Yeah.
Okay, cool. It's been a long time. Like, you have it on there, you spin that bad boy, and you make a cylinder, and then you start, like, just kind of boring out the inside, right? Like, your cup in your hand, and you're kind of boring out all the guts of it, right? That's really what's happening here, right? Except it's sideways, so it's a little bit different. But you have a cylindrical piece, and then as it's being spun, you're boring out all the beef on the inside of it. All right. Beef sounded better than guts, so that's why I went with that. So I'm going to have, on the interval of 0 to pi over 2, I'm going to have a pi r squared. Now, the r would be the y for this function. So I can color code mine, so I'm perfectly fine just saying pi y squared dx. And then in the second part, subtracting off the part that I don't want, on the interval of 0 to pi over 2, writing the exact same thing, pi y squared dx, because I've color-coded my stuff. Now you should probably, if you're not color-coding it, and you won't be doing that on the AP, use subscripts, y sub 1, y sub 2, all right? This allows you to generalize your rule, and then after that, you're in pretty good shape. Because if it's a calculator type question, let statements are a beautiful thing. Because I can define this up here right in the problem, or maybe below it. I could say let y1 equal 1, let y2 equal sine of x, label up my diagram with those subscripts, label my integrals with those subscripts, and then just report the answer. without ever having to write what the functions are out on paper. Now, these aren't crazy functions, but you could be dealing with some pretty complicated functions. To have to write it on paper and also type it in your calculator, it takes time, all right? Maybe time that you don't want to spend, all right? So subscripts are a good way to go with that, all right? So now I want to get specific because I'm doing it by hand. Pi times the y value for the red rectangle is 1, so pi dx. And the other one is sine of x, so we're looking at, on the interval of 0 to pi over 2, pi sine squared x dx. All right, so the first part's really easy. The second part, well, you have to involve a trig identity substitution. So the first part, you're integrating a constant function. So the shortcut that we learned for that is that you just multiply your integrand by the difference between the bounds, in which case you're going to get pi squared over 2. Also, you might consider the fact that this will actually be, if you take a horizontal line or a line that's parallel to the axis of revolution and spin it around, it creates a cylinder. And so that cylinder has a height of pi over 2 with a radius of 1. So using pi r squared h, the volume of a cylinder formula, you can figure that out too. All right. The other part, we have to do our substitution. So minus the integral going from 0 to pi over 2, pi times, what's the substitution for sine squared? One half, the 1/2 thing, 1/2 minus cosine 2x. All right, so pi squared over 2 minus the integral on 0 to pi over 2 of pi over 2 minus pi over 2 cosine 2x dx. So pi squared over 2 minus, then we're going to have pi over 2x minus, what's the antiderivative of pi over 2 cosine 2x? Pi over 4 sine 2x on 0 to pi over 2. We just have to clean that up a little bit. The good news is the 0 part is irrelevant because that's going to 0 out on the inside. So we're going to have a pi squared over 4. So pi squared over 2 minus pi squared over 4. Plus, oh, no, 0's out, right? Because pi over 2 times 2 is pi, and the sine of pi is equal to 0. So a half minus a quarter is a quarter, so we're talking pi squared over 4. Only complicated because you have to do it by hand. All right. So the general rule for this really just amounts to doing the disk method twice. All right. But you could kind of clean it up because you can see that the bounds of integration are the same. You can see that each one has a pi in it. So those are things that can be accounted for. So if you really want the most general form of it, what we would say is that we're looking at pi on the interval of a to b times the difference between the squared radii. So I'll do a capital R for the outer radius minus lowercase r for the inner radius, d something, right? So d, I'll put a box there because it could be x or y, depending. All right. So the next one, and really the last one, region enclosed by the graph of y equals x squared. The line x equals 2, and the x-axis is revolved around the y-axis. All right, so your diagnosis really just boils down to whether or not there's a gap, a null space between the axis of revolution and the bounded area. Right? There's a part that we don't want to be included in the volume itself, so it needs to be subtracted off. That's your clue that you're dealing with a washer method situation. All right, so I need an arbitrary rectangle for the outer function, and I need an arbitrary rectangle for the inner function. So x dy, x dy. And as long as you can keep straight which is which, the outer one is x equals 2. All right, so maybe make a note of that on your rectangle if you want. So x equals 2. The inner one would be what? X is equal to what? Well, y is equal to x squared, so x is equal to square root of y. All right, so we would say on the interval of 0 to, now this is in terms of y, so what would be my upper bound? I know I'm going from 0 to 4. So pi times the difference between the squared radii. So 2 squared minus square root of y squared, which you could just write as y, dy. So that cleans to 4 minus y squared, sorry, y, which integrates to pi times 4y minus 1/2 y squared over the interval of 0 to 4. 0 is irrelevant. Pi times 16 minus 8. So 8 pi.